This is our Target Identification and Object Detection Device, or TIOD for short. It was designed to complement modern computer vision technologies, which often struggle in low visibility conditions. By operating with radio frequencies instead of light, the TIOD can see where cameras and LiDAR cannot. This capability makes it a valuable tool for a wide range of applications, including autonomous vehicles, smart manufacturing, infrastructure, defense systems, and much more.
Let's walk through the different concept development options we evaluated using the Atom-Pluto system. In option A, we use the pre-existing Atom-Pluto antenna with a supervised machine learning model and the power of the system with the battery. This configuration is designed for portability and simplicity. Some of the advantages include leveraging the Atom-Pluto's built-in antenna reduces the overall system's complexity. A supervised model is easier to program and offers higher accuracy when recognizing known objects. Using a battery makes the device portable, ideal for mobile users. However, there are a few trade-offs. The built-in antenna may limit result accuracy. A supervised model can't classify unknown objects, limiting adaptability. Batteries add maintenance overhead, needing to be recharged or replaced. In option C, we again use the Atom-Pluto antenna, but this time with an unsupervised machine learning model that still relies on battery power. The advantages are lower design complexity by using the existing antennas. An unsupervised model enables the system to classify objects that hasn't been previously trained on, adding more flexibility. The battery also continues to support mobility and field development, but some of the downsides includes the same antenna's limitations could reduce its performance. Unsupervised learning could add complexity into the implementation and reduce classification accuracy. And again, the battery reliance brings up logistical challenges. Option D keeps the Atom-Pluto antenna in the unsupervised model, but switches to a USB power port for power instead of the battery. The key benefits in the setup are a lower system complexity by using both the Pluto antenna and the USB power source. The unsupervised model provides flexibility in object detection. The USB power simplifies the power design and reduces battery management. On the downside, portability is limited since the device must be plugged in during use. Like before, the antenna could restrict accuracy, and the unsupervised model can increase the design and programming burden. And finally, option E, which uses a custom design antenna, a supervised machine learning model, and a battery for power. The advantages include a custom antenna can improve accuracy and detection range. Supervised learning offers easier programming and high accuracy for trained objects. Battery power gives the system better portability. Some of the disadvantages include designing a custom antenna adds more complexity and development time. The supervised model can only identify objects it's been trained on, and the batteries require recharging or replacement, adding maintenance or complexity. After reviewing these design concepts, we ultimately selected option B, which provides the best overall balance between accuracy, simplicity, and reliability. It allows us to focus on effective classification with a controlled environment while minimizing system complexity and development time.
To use the device, simply plug it into your computer using the provided USB cable. Then aim the device towards the object that you wish to identify. The TIOD is able to identify these objects thanks to the method used to train the machine learning model.
To build this model, objects were placed on a rotational mount in front of the TIOD, and reflected signals were recorded at 15-degree intervals. These measurements were used to train the model to learn relationship between signal strength and angle of incidence.
Using the trained model, the device can detect and identify objects of different shapes and sizes, both quickly and accurately. Additionally, it's completely controlled through a user-friendly interface. Since our device uses radio frequency transmission instead of light, it has the ability to see what cameras and LiDARs cannot, allowing for the detection and identification through darkness, smoke, fog, and other poor low visibility conditions.
Inside the case, we have two LPDA antennas. The transmitter and receiver are both isolated to prevent coupling. These antennas are controlled by the Pluto software-defined radio, which was also meticulously isolated to prevent internal reflections. The final result is a small portable device that can distinguish between various differently shaped objects. In summary, our device successfully demonstrates the capability to identify metallic objects of varying shapes in real time. As a prototype, it highlights the potential for future development and scalability towards detecting and classifying more complex objects with similar accuracy.